All right, good afternoon. I apologize for this slight glitch with the projector, but I think we are now all good. There's some little feedback here. Let's get a little bit down. Good. Good afternoon in the classroom. Good afternoon, everybody joining us remotely to the Materials Resource Sustainability Nexus seminar. I feel I still get a little bit of feedback. Is it okay in the room? Okay, thank you. So we run again the Materials Resource Sustainability Nexus seminar, both as part of the class Materials Resource and Sources and Sustainability, and also as a seminar with guests coming from outside. After my introductions of our speaker, and our speaker will talk for 40 minutes here in the classroom, and then we'll have a quick break. And there we will have time to discuss questions at the tables here. Online participants have the option to join a breakout room. They might also just stay in the main room and then come back for the full Q&A session that follows that. So, and with this, it is my great pleasure to introduce our speaker today, Dr. Virginia Gillerman. Dr. Gillerman is an economic research geologist with the Idaho Geological Survey, which is part of the University of Idaho. She received a PhD from the University of California, Berkeley, and a Bachelor's of Arts from Carleton College. She spent 9 years in the mineral exploration industry before moving to Boise to staff a new one-person satellite office for the Idaho Geological Survey in 1989. She is also affiliated faculty in the Geoscience Department at Boise State University and taught an occasional course in past years. With the IGS, Dr. Gillerman has had multiple responsibilities, including answering public inquiries on ore deposits and the geology of southwestern Idaho, the annual mining and exploration review, and conducting research on mineral deposits. Examples of her projects include geologic mapping in the Mayfield, Hagerman, and Delamar areas, inventories of abandoned and inactive mines, rare earth and thorium in the Lemhi Pass district, gold and antimony in the Stibnite Mine district of central Idaho, and the Idaho Cobalt Belt and Lemhi Pass rare earth belt in Lemhi County. So with this, Dr. Gillerman will talk to us today about basic aspects of mineral resources, geology, engineering, economics, politics, geography, some Idaho examples. Please help me welcome Dr. Gillerman.
Okay, we'll put this down here. And try that. Does that sound, everybody hear me? Okay. Thank you for having me. I'm a geologist, specifically an economic geologist, and we're gonna just get started. You can hold questions till last, or if there's something important or you really don't understand it, just raise your hand. We just covered that. We're going to talk about mineral resources, what they are, some basic concepts and different definitions, a little bit of basic geology, and some of the economics and environmental aspects of the mineral resource industry, with most of the examples from Idaho. I think you heard some of this last week. Why do we need minerals? Well, these are the basic raw materials for pretty much everything you use in your daily life, along with timber and a few other natural materials. But we're going to limit our discussion to geologic materials. We'll just call them minerals. That includes iron, lead, gold, wiring. It includes things like non-metallics like phosphate, gravel for concrete and road building. All sorts of things that you probably don't think about are in the table you're sitting at or your computer. Why is this important? Well, back in the Stone Age, we didn't have 8 billion people on the earth, but we do now. And I'm not going to suggest a way to get rid of them. So if you don't want to go back to the Stone Age, we're going to have to find some raw materials to support our current lifestyle. And hopefully one of you engineers or somebody in this room will devise some hugely new way of doing things so we don't have to waste so much stuff. The mineral industry is actually pretty complicated, and this is from the annual mineral commodity summary that the U.S. Geological Survey puts out. I have a hunch it may be delayed this year. But it talks about exports and imports, and oftentimes the country will export and import the same commodity for reasons that are bizarre. It includes recycling, it includes scrap that's converted, or maybe it's exported to some other country that recycles it. So it's the thing about mining and mineral resources it's a global industry, it's a global process, and we can't really get away with that. This is from the 2024, which means estimated values from 2023, and they put the U.S. gross domestic product at 27 trillion, with minerals values added at just under $4 trillion. So that's another whole talk in itself. But just to point out that it isn't just mining, it includes processing, import, export of all kinds of commodities, as well as recycling and scrap materials. You may have heard a lot of discussion lately about our net import reliance, particularly in regard to China. This is a pretty famous graph that the USGS has put out for years, and it's kind of nice to compare it. If you want to go back and look, you can find this on the web. For example, in 2017, rare earth elements were imported at 100%. So the United States was 100% reliant on those imports. The blue bars that go all the way to the right on the screen, that's the 100% mark. And as you can see, there's quite a few that are, if not 100%, pretty close to it, over 50%. For example, I don't have a pointer, but yeah, rare earths on the 2023 is down about 12th place. Something like chromium is 74% imported. Even some abrasives, which you don't think of as particularly sexy or on the list, vanadium, etc. Some of the methods have changed, so we're not going to worry about 78 versus 80%. And it includes a mix of raw ores and refined materials. The concern politically has been about China, but other countries are in there that we're not super friendly with. And if you looked at a lot of other countries historically, you could find similar historical concerns. In some cases, those historical concerns have led to world wars. So it's not trivial. We have, unfortunately, an excellent example of why you should pay attention to politics and public policy. If you haven't heard, the president froze all federal grants and loans, which includes our agency's grants for critical minerals research. That's effective as of about 10 minutes ago. And it also includes probably a lot of healthcare, Medicaid, other scholarship and education programs that are funded by the federal government. So politics can control minerals, but it can't control where they are. And we're going to get into the other things that do. I gather Travis explained, well, okay, on the globe map, the red areas are where we import a large number of commodities, followed by the orange areas. And as you can see, production is scattered across the world. Some of the things, as we go through the talk, the Defense Department is particularly concerned about because it's all in their airplanes and weapons. But it's also in your hybrid cars, your wind turbines, particularly the rare earth elements. Is anybody in here a chemist? You know what rare earth elements are? I didn't put in the, I'm sure it was explained last. Anyway, a group of elements on the periodic table with similar properties, and they're in very small amounts in every single one of your phones. So you may not care about the fighter plane, but I'm sure you care about your phone. If you're in the Army, your special forces gear has a whole bunch of stuff, and there's some pretty nifty examples of how rare earths are used in military applications. There's something about your smartphone. One of the things which is not officially a critical element, and the US has provided a list of, I don't know, 40 elements, it keeps rising at 25, that it considers official critical minerals right now. They're actually elements for the most part, but the politicians don't know a lot of science. But one of the ones that's not on there, but is still getting a lot of attention, is copper. It's a pretty standard, common base metal. And one of the reasons is copper is our standard best conducting material for wires and to transmit electricity. So whether it's the electricity in your house, the electric wires that form the basis of your automobile, or a whole host of other things, copper is key. It's actually one of the metals that the US produces quite a bit of, but at the rate we're going, if we all switch to electric cars, we're going to need a lot more copper. And so for a metric ton of copper, you can produce 44 conventional Jeep Cherokees, but only 12 electric vehicles. So that's a big concern as we try to electrify everything. Okay, let's back up and look at some basic geology. What is anybody in here a geology major? One, okay. A mineral is a naturally occurring inorganic crystalline phase, and it consists of atoms of whatever they are, arranged in an ordered structure, usually a crystalline structure. It's inorganic, and it doesn't include things like desks or technically glasses. A rock, in contrast, is a collection of minerals. So a granite, like we have up at the ski area, is a collection of the minerals quartz, feldspar, and mica. Other rocks, common rocks, are basalt, also known as lava rock around here, or quartz vein. Some other key concepts are resources, which can be defined as computable wealth or immediate and possible source of revenue, and then specifically a mineral resource or deposit, which is a volume of rock enriched in one or more minerals, whether it's economic or sub-economic. Most of these formed over 10 million years ago. Another key thing to think about is renewable resource versus non-renewable resource. So if you have a rock or a mineral deposit that formed 150 million years ago, and maybe it took a couple of million years to form, is that renewable or non-renewable in our lifetime? No, it's a definite not. If you have a field of corn and it can get harvested and regrown every year, that's renewable. So crops, cattle, timber, those are renewable, but any kind of earth material is really non-renewable. More particularly to mining, an ore is a rock or mineral that can be mined, processed, and delivered to the marketplace or user at a profit under current prices and technology. And that's true whether it's sand and gravel, gold, garnet, or metals such as copper or lead. Today, I can also say no permit, no mine, no ore deposit, due to ESG, which is environmental, societal, and governance factors. And that depends in part on which country you're in. But basically, nobody's going to want to mine something if they can't make a profit at it. Unless the politicians say, oh yeah, I'll pay for it. or you have somebody pointing a gun at your head to, break that rock with the prison gang. Or therefore, ores are very special and unusual rocks. They're uncommon and they're very hard to find. And it's the mineral exploration geologist's job to find them. Another important point is that mine production is not constant, neither are metal prices. So this is a graph of production of silver from North Idaho mines in the blue bars versus price in the orange line. Unfortunately, what often happens is when the price goes up, the mines increase production, or somebody goes out and discovers a new one. At that point, supply is higher, and so the price goes down. And and then there's a whole bunch of other reasons why prices fluctuate, but it makes planning very difficult. And again, it's controlled by the marketplace. It's not really controlled in most situations by any government or wishful thinking, although there's plenty of that in exploration. So when we talk about an ore deposit, technically that's one that can make money. Only about 1 in 1,000 of mineral deposits, which is a more generic term, can actually be converted to ore bodies. Phosphate is Idaho's largest mineral industry, and we'll talk a little bit more about it. But just as an example, phosphate is localized in Idaho, in southeastern Idaho. It provides direct employment for probably 2,000 people, as well as producing useful products like fertilizer and food additives. There's a picture of one of the mines, Blackfoot Bridge Mine, owned now by Bear. And it's a fairly large operation, but it's probably would be considered a medium scale mine. But that ore goes into not this plant, but another one. We have 3 processing plants in southeastern Idaho. And that's where the product that you actually use is made. So this is Simplot has another mine I'll show a picture of later. Their ore goes by an 87-mile long pipeline to this plant in Pocatello. And if you've driven past on the freeway into Pocatello, you've probably seen it. That's where the bulk of the workers are employed, is in the plants. And that's what is needed to actually go from the rock to a useful commercial product. One of the things I do each year is sort of do a summary and a survey of mining and exploration activity around the state. So these are maps from this year's presentation given last December. And I haven't counted up the dots on the exploration map, but exploration is where geologists and companies go out and try to find areas with a mineralization, and they hope that they might convert them eventually to a mine. If you look at the number of dots, maybe there's 50 or 60 on there. If you look at the number of active mines, there's about 5. And some of those were discovered 100 years ago. So typically, when I was in exploration, we would sort of say, well, you're going to have to look at about 1,000 prospects to find one that might become a mine, if you're lucky. So that's exploration. If you find something, and we'll go into that a little more detail, then you can mine it if it's economic and if you can get a permit to do so. The ore from that mine has to be milled into what's called a concentrate, and we'll look at that. And then that concentrate is often sent to a refinery or a smelter, depending on what type it is. And that is where the metal or the sort of pure material is produced, which then goes into a product like your phones or the wallboard in your house. So that product goes to the consumer. You use it for a series of months or years or whatever, And then maybe it ends up in the landfill, or hopefully it gets recycled. All of that's part of that sort of life cycle of mineral materials. What's a mine look like? Here's a view of the Galena mine in North Idaho. It's an underground mine. There's what's called the head frame, and it's basically has a wheel on the top with a cable that controls the elevator, or also called the hoist, that goes down, in this case, over and down to about 5,500 feet below below the surface. The deepest mine right now up in the North Idaho is the Lucky Friday 4 shaft, and that's down about 8,600 feet below ground surface, actually in 2 different segments. Things have changed a lot since the photo on the top there. Mining, both underground and above ground, is totally different than it used to be in the late 1800s or the early 1900s. They don't use single jacks, they use big drills, they use loaders to muck or to carry waste or rock, crushed ore, diesel, or in many cases, some of the bigger mines are now shifting to underground electric vehicles. Another example in North Idaho of a small underground mine is Idaho Strategic Resources Golden Chest Mine at Murray. Murray was one of the old placer districts, so they discovered placer gold, which is gold that's been transported through water in a stream. They have some veins there, which you can see in this picture. They're basic quartz veins. That quartz is the white material, it's silicon dioxide, and then you see visible gold in that particular shot. The entrance is called a portal to the adit. The adit is usually a subhorizontal tunnel. Some of their grades up there, good grades in one of their veins, is 10 grams per ton. And 10 grams, the count is about 1/3 to, well, the grade varies, but it could be like 1/3 to 2 troy ounces per ton. So if a ton is 2,000 pounds, that's not a lot of gold in that volume of rock, which means that you have a lot of waste material. After you get the gold out of the quartz, you have a lot of waste material, and you might have to mine some of the wall rock, the black stuff around it. What they do with their ore is they take it to a nice small mill, Kellogg, shown in that photo. The white area above the mill is what's called a tailings pond, and so that's been dried out, and that's primarily, in this case, crushed quartz material. And notice that it's got a pretty nice berm around it so as to not have any escape to the environment. The other type of common type of mining is open pit mining. And here's a fantastic example. This is the Bingham Canyon copper mine near Salt Lake City, Utah. It's what's known as a porphyry copper deposit because it's in partly in a rock called a porphyry, where you have large crystals and smaller crystals combined. The natural concentration in their ore is approximately 0.5% copper, which is actually pretty good, versus a normal rock, which would have 50 parts per million of copper in it. In addition to copper sulfides, they also produce molybdenum, gold, and tellurium. It's one of the largest mines in the planet. And some of these large open pits process 50 to 100,000 tons per day of material. They have a mill there. They also have a smelter, which you can see it's got a large stack right next to the freeway. And if you've noticed, it's one of the most environmentally clean ones around. You rarely see even water coming out of it. They also have a refinery that produces pure copper, ingots, wires, whatever. Open pit mining there started in 1900. And it was the recognition, it was actually one of the birthplaces of open pit mining. If you have to make a profit at your mine and you can only mine like a narrow underground vein, you're going to have a lot higher grade or content of, say, gold or copper in that rock than if you can mine 50,000 tons a day. So what a guy named Jacklin figured out around 1900 was, well, in this type of deposit, the veins are thin, and maybe the grade's only 0.5% or even 1%, but they occur over a very large volume of rock. And he said, and in this case, it started at the surface. What if we just take out, bring in big shovels and we mine a large volume instead of going underground and trying to mine the big veins? And it worked out. And many of the copper mines around the world are open pit mines, and they're needed to produce the large volume of copper that we use today. Just to look a little more detail at the steps in a mining project, if you were in the industry, you might start with a market review, some geologic research, exploration, which includes looking at the geology, land acquisition, doing some geochemical and geophysical surveys to add extra information to where you think the ore might be, because it's rarely outcropping, especially nowadays. And then you have to get federal or state permits to drill, there's a picture of a core drill in Lemhi County. And you do a lot of drilling, like thousands of feet, thousands of meters. And then you can do your economics on it and get the financing, raise $1 billion or so to put your mine in. Mine permitting can be, say, 25 to more permits in this country. It's done under, typically, if it's federal ground, especially under what's called NEPA, or National Environmental Policy Act. And it produces an environmental impact statement that can take 5 to 30 years. After you get the okay, that's where you start your serious engineering and mine planning. And that's all extremely high tech. In fact, even the exploration, they will take the drilling results and put them into a 3D computer model that you can turn around and on the screen and do all kinds of stuff. Then you have to actually mine it, which is pretty high tech, but also depends on important things like truck drivers and the seconds, is the truck driver going at the right speed so they get the maximum number of hauls in their shift, or are they just kind of screwing around and taking a break, and then you're losing time and you're losing money. The truck drivers will take the ore to a mill, and then that will eventually go to a refinery. The next stage with mine closure, and often before mine closure, is reclamation. And that's pretty standard these days. Another, well, probably the largest open pit in Idaho is the Thompson Creek molybdenum mine. It's used for jet engines, alloys, lubricants, etc. This is a good example that shows how industry changes over time and how it's affected by other things. This mine near Clayton, I think it's produced about 500 million pounds of molybdenum. It closed in 2014 when moly prices were about $10 a pound, and also some other corporate complications. They have a big on-site mill we'll look at. Last year, the moly price was up, and this year it's still up. It's about $30 a pound. And the company evaluated its options, and they commenced stripping on a restart of the mine. They'd already had drilled out a reserve. They call it phase 8, which is below the bottom of the pit. So, and that's water in there because the water fills in once you stop pumping it. This year, they committed full feasibility or economic analysis suggested that was going to be a good move. They've now got 145 employees and expect production in the middle of 2027. Now, the reason it takes a couple of years is because to get the ore in the bottom of the pit, they have to do what's called a pushback or a stripping operation of that face of rock there, because you have to have a certain slope on your rock or you're going to have engineering failures and rock stability problems. So it's a 2-year stripping operation to get that ore for their next phase. That's an old photo with a student tour at the mine, but you can see the size of the trucks that they need to haul that much material, whether it's ore or waste, out of the pit. In the mill, what they do with the ore, the rock, which is relatively high grade, I think it was running about 0.2% molybdenum. So again, not very much. So you have a little bit of ore or a little bit of metal and a lot of waste rock. The first step is to put it into a ball mill, which is like a giant tumbler with big steel balls. They rotate, crushes it up, uses a lot of electricity. Once you have your ore crushed to almost a flour-like consistency, they put it in a flotation cell, which looks like a series of giant bathtubs with a surfactant added that will float the sulfide material. It's kind of flaky. And so that floats into sort of bubbles that they'll skim off and dry. And that's the concentrate. The quartz in the rock and the other minerals will sink to the bottom of the bathtub. So they'll put the concentrate in a bag or in drums, and then they ship it to a roaster in Pennsylvania. And that's where it's converted into molybdenum metal and other products that they could sell. The crushed waste rock, the tailings, which are called the tailings, goes to their tailings pond, which not a great picture of the dam, but this is the face of the dam, and it's pretty big. I think it may actually be the largest dam in Idaho. This is backing up a little bit. So the different metals and materials are concentrated in different minerals. And if you've ever been to a museum and looked at their mineral collection, they often have it arranged according to different chemical classes of minerals. So most easy to explain are the native elements, gold, sulfur, sometimes copper metal. Those are formed as naturally as native elements. Diamond's an example, but so is graphite, same composition, different physical structure. Some things like iron and chromium are concentrated in oxide minerals, also tin and aluminum. Other minerals, other elements like iron, lead, copper, go naturally into sulfide minerals. They're what's called chalcophiles. And so typically we get our base metals from sulfide minerals, but also some things like silver. Those are often deposited by water-rich fluids, aqueous fluids. We call them hydrothermal fluids. Industrial minerals are typically maybe chlorides like salt or phosphate or phosphates or carbonates. And then there's some others listed there as well. So you have to know your mineralogy if you're going to look for any of these commodities. And that's the primary geologic control on where you might find any one of these elements. What about the mineral deposits, which are the enriched concentrations of these various elements. Well, that's a couple of about 5 classes worth. So we're just going to skim over it. You can see here, many ores, as I mentioned, are particularly veins, are what are called hydrothermal, i.e. deposited by fluids, water-rich fluids moving through cracks and fractures in the rock. Some things like chromium are, or some types of nickel deposits are also related to magmatic processes. We can talk about that later. But regardless of the process, what you need is a concentration over its natural abundance. And that, it's called the Clark factor. But anyway, there's a whole host of ore forming processes, many deposit types. Some of those deposit types are keyed to specific geologic environments like mountains or large sedimentary basins. And sometimes they're also keyed to specific periods in geologic time. But the big deposits are extremely rare, and we don't understand all of their reasons why they're localized where they are. But again, they're non-renewable over our lifetime. So looking at some examples from Idaho, we have a pretty long geologic history. I think we'll skip this. Some more on the phosphate district. This is related to a 265 million year old black phosphatic rich shale, which is about 25% P2O5 and also enriched in trace elements. We have a project going on to look at some of those. Phosphate is our largest portion of the mining industry in Idaho, and there's presently 3 mines and 3 large plants in operation. 2 types of plants, fertilizer and an elemental plant. Shows one of the mines with some of the different ore horizons or geologic units indicated. It's pretty fine-grained, ugly black rock, but it pays the bills and it employs quite a few people. It's the remains of a sea that formed about 260 million years ago, called the Phosphoria Sea, extending over what's now a 4-state area. We also have silver in Idaho, and this is a global map, just shows some of the different types of silver deposits. The Coeur d'Alene is in North Idaho, up near Wallace, and we'll look at Delamar as well. These are some of the rich silver minerals in the Coeur d'Alene. Galena, which is a lead sulfide, which has silver substituting in it. And then tetrahedrite, which is the sort of ugly bronze blackish material over there, which can have up to 400 ounces per ton of silver in that lattice. So not exactly gem material, but pretty nice stuff. The Coeur d'Alene has produced over 1.25 billion troy ounces since 1884. Probably ranks in one of the 10 largest silver districts in the world. Native silver, there's a specimen I bought, native wire silver, can look like that. But more typically in some of the veins, the tan material here is siderite and iron carbonate. It's part of the waste rock. And then that little bit of brown stuff, darker stuff, is the tetrahedrite, the silver, copper, antimony mineral. There's over almost 100 mines in the Coeur d'Alene. We have 2 operating right now, the Galena and the Lucky Friday. Geology is extremely complicated and interesting. These are not random occurrences. They're structurally controlled by folding and faulting, as well as the age of the basin. There's a number of different geologic types of gold deposits. We'll briefly look at a couple in Idaho. This is what's called a Carlin type deposit after a huge district in Nevada near the town of Carlin. But this is in Cassia County. It's the Black Pine Mine, now a project of Liberty Gold that's probably going to reopen it. Really ugly rocks with no CM gold. The gold is micron size, and but it's pretty important. A classic Idaho deposit is the Delamar Florida Mountain District in Owyhee County, about 90 miles south of here. These silver deposits are associated with a series of 16 million year old volcanic rhyolite domes. This is a simple cross section. The different colors represent different volcanic rocks. But just to show you typical exploration, the red are the veins, some of which were mined by the old timers underground. And then the black diagonal lines are drill holes with specific intercepts from modern exploration. And so the exploration geologist is trying to guess the geometry underneath the earth and find those things. It's pretty challenging. That's what one of the small pits looks like on the surface. And an example of one of their crustiform hydrothermal quartz veins with silver sulfide, which is the blackish material, and some pyrite in there. So again, it's challenging to find, targets like that with a drill. We're going to skip that. Cobalt, we have the Idaho Cobalt Belt in Lemhi County. Cobalt is primarily sourced right now from the Democratic Republic of Congo, and it's been fairly controversial because some, but not all, of their cobalt is produced by what are called artisanal miners. There's a picture of one, and well, it's easy for us to think that they're being abused and there's 14-year-olds that are miners. That's also the only way they have of really making a living over there in some cases. However, a lot of the ore is actually produced by modern mines, many of which are in part owned by the Chinese. Some are owned by international companies. And if you looked at the newest one, it would be totally high tech. Idaho's cobalt belt, in contrast, has some geologic similarities. There's the town of Salmon. The green squares are different cobalt deposits associated with copper. Again, complex geology. Some similarities to, but a lot of differences to the African stuff. The main mine at Blackbird was taken over by an Australian outfit called Jervois Global. And in 2022, they had a big hype. They were going to open a mine, the Idaho Cobalt or ICO mine operation. The governor, ambassadors, various dignitaries were up there to help open the mine, which would be the only U.S. cobalt mine. They were very optimistic. A lot of work had been done, but relatively small resource. Things didn't work out. The price went down. So the mine never actually opened. They closed it in 2023 in March. This last year, they were still on care and maintenance, although they did do some drilling with money from the Defense Department. There's some of the surface mills that have already been constructed, a couple of portals and some underground drills. So it's not easy. Reclamation is required. This is the Bear Track pit mine reclamation in Lemhi County. All of that flowery area formerly was an open pit. I think I'm running short on time, so I'm going to kind of skip this. Examples of reclamation in the phosphate district. The companies, along with many agencies, have been working hard to minimize any downside from trace elements in the phosphate ore. Stibnite, a controversial project you might have heard about in the media, started its permitting in 2016. The record of decision was issued last month, actually maybe this month. World-class gold antimony deposit, again, would be the main U.S. antimony or the only sole source. It's going to be probably sued, but anyway, we can talk about that. The black crackly stuff in there is the sulfide stibnite, the antimony sulfide. People like mining and some people don't like mining, and we can talk about it. Sustainability, what is it? Is it really just jargon, or is it something about, as some UN says activities that meet the needs of the present without compromising the ability of future generations to meet their own needs. It's fairly idealistic, but it is a term that you hear about it. Good mine reclamation is critical. What exactly is it, and who pays for it? So just in summary, some basic concepts: geology rules, its location. Economics is really the determining thing, and a lot of that is influenced by engineering, material science, and technology advances. If nothing else, I'd like to mention that the mineral industry has a whole lot of different career opportunities. Just technical. A truck driver for one of those haul trucks in a big mine could make $100,000, and they deserve it. So don't, everything from environmental hydrologists to accountants to engineers, all of those kinds of careers are in the mining industry, and it is a global industry. That's it. Thank you.
Thank you, Dr. Gilman. And for you, we have now a couple of minutes break for us here in the room, and also for those online. For those online, you're free to join a breakout room if you want to do this. There's just one where you all will discuss the slides. That is the next slide. I'll just forward this here, where we have our discussion prompts. Online, if you just stay in the main room to wait for about 5 minutes for having the open Q&A, that's all right also. And here in our classroom, we'll just sit in our groups, in our teams. So if you want to just the front row, my back row, and discuss these questions that we have up here, and we will make them visible in just right now. Let's move these things away here. So if you want to talk about these 3 questions for 4 or 5 minutes, and then we'll have time for Q&A for Dr. Gillerman. Aha, like Christmas, it works. So I don't know, I don't have oversight over the breakout rooms and the online, but if those folks want to join back in, that'd be great. And so we have now time for questions for our speaker, Dr. Gillerman. If you want to come to the front, please. And who would like to start us off? In the back row, and I'll bring the mic. Or maybe you can shout loud and I can hear it.
Okay, the question was, how much does it cost to process, say, a ton of material like the molybdenum mine, which has maybe 0.2 or 0.3 or something percent moly? They hire a lot of engineers and economists and project managers to figure that out. It depends on the place, but if you're, and I don't deal with that, so I'm really not up on the latest. And obviously, just like going the price of eggs, it varies. I think an underground, I think an open pit mining cost, you're probably looking, geez, I don't quote me on this, but I mean, we're talking like $30 a ton or $5 a ton. If you go through company reports in detail, you can sometimes figure that out. And there's a whole bunch of different accounting practices. It costs a lot more money typically to process a ton of material from underground, because if nothing else, it's physics. If you're mining ore that's 5,000 feet underground, you got to lift it all the way to the surface, and that takes a lot of energy. If you're in a deep open pit, you have to truck it up to the surface and over to the mill, and that takes energy, and energy costs money. It also takes equipment, and equipment costs money. If you look at, like, if you're walking around central Idaho and you're looking at old mines, they would usually structure the mill on a hillside so they could take advantage of gravity. And so they put the ore at the top, and it would go down through the different processes and be gravity fed down to the end. Oh boy. I don't want to say anything too specific because it depends on the property, but that's one of the key factors when they do an economic analysis or a feasibility study before they go from exploration to a production decision. That's one of the key things they look at. And there are handbooks where you kind of get a general idea. The cost of processing a ton of ore in central Idaho is going to be a lot different than if you're in central Indonesia, where your laborers get paid $5 a day or something. So it really depends on a lot of factors. And I'm sorry, I should be able to answer that, but I'm gonna.
You answered it actually very well. Different complexities that are here. Other questions? Yes, please.
So my group was talking about sustainability, and specifically, how do we define a stronger definition of sustainability? We weren't satisfied with the United Nations definition. We felt we left out kind of what we felt was sustainable, what we felt was kind of natural aspect of beauty. And kind of the question that I thought of when we were talking about this was, would this be unacceptably too expensive for any or all mining companies to do the sustainability practice?
Well, yeah, the question dealt with a better definition of sustainability, and is it going to be expensive for companies to actually do it, or too expensive? There's a whole bunch of different definitions of sustainability. And so I just, in the interest of time, I just mentioned one, the Integra one, leaving a resilient and prosperous community with a net positive legacy for local economies and communities. That's great. Colorado School of Mines, which is one of the few schools left in this country that actually has like a full mining school. They break it into different aspects: environmental, economic, societal, public policy, and technology, which kind of sounds reasonable. It can be expensive, and I don't think everybody would agree on a definition. However, there are various corporate sort of global initiatives to have companies sign off on a global definition or subscribe to the UN Commission or something. It can be really tough, and it's actually probably just as tough on the social aspects. If you look, for example, at the fracking industry in places like North Dakota or something, they've been accused of kind of going in and high grading or taking all the oil out and then bringing in a whole bunch of roughnecks and oil people without the social structure. And so it kind of, then when they leave, there's this void and all kinds of negative social impacts. And you could certainly say that, you know, true of mining and maybe indigenous groups or local economies. So in some cases, you could say that putting the landscape back, so it's maybe not quite the way it used to be, but it's at least not degrading the landscape. That can be done. The hardest thing is often water quality. If there's some kind of, no matter how good your system is, you may have to do some water treatment on a more permanent basis, and that does get expensive over the long term. Some of that, it's really site dependent. Things like, you know, returning the landscape to recreational possibilities, or a lot of gravel pits are now subdivisions. You know, they fill in the gravel pit with water It's a lake. They build $1 million homes around it. That's considered sustainable if you have $1 million. If you just leave a mess and you expect the local inhabitants who formerly had a subsistence way of life, but now they just have this huge mine wasteland and wherever, that's not sustainable. The problem is getting the consumer to pay for it. And that's an economic, they call them, I think, negative externalities in the economics profession. It's really, really hard to get the consumer to pay for those. Especially, well, I'll leave it at that.
Excellent question so far. There's one more over here. Yes, please.
Yeah, so when it comes to reclamation efforts, is it mostly a consideration of we're going to come in and mine and get the resources, and then afterwards it's going, like, we're going to reclaim the land, we're going to work on it, or is there consideration during the process, or like anything built in to make it easier to reclaim or to reclaim while mining?
Good question. The question was about reclamation, and is that simply done at the end, or is it sometimes done during the initial stages of the process, in which case you have an opportunity to make some tweaks that might make it easier? It depends on the operator, but often in this case, in 2024, 25, most companies realize that they have to think about reclamation before they even start mining. And in some cases, like Perpetua's Stibnite project, one of the reasons that they're arguing they should be able to mine the gold is because it will pay for a large reclamation project and restoration of the watershed of that river, and some of the cleanup of historic mine legacy waste. So reclamation was typically not even thought about until about the mid 1970s. I think it was the Clean Water Act was 74, I want to say. Basically, like up in the Coeur d'Alene, they just put most of the tailings into the river. River flushed them downstream. Everybody did it. Didn't matter if it was sewage waste or mine waste or whatever. That was simply the practice at the time. And needless to say, we don't do that anymore. That is not legal. Some companies, yeah, are better than others at thinking ahead. And there's a lot of local, technical, geologic, ecological, geographic constraints that dictate any particular site. But most companies will at least try to think a little bit ahead and as they plan their mine. And the mine planning, I mean, they've got engineering design, 20 years out. And then they tweak it. It goes through a whole bunch of different stages and stuff in a modern operation. Okay.
So we kind of learned in the last seminar that in the United States, we don't really mine more than one metal at a time, like processes are tuned for a singular metal. At Stibnite, they're doing antimony and gold, right?
Right.
Is this one of the first times this has ever happened in the US?
No, I'm not sure that that's quite what the last guy meant about mining one metal at a time. There are a lot of mines, a number of mines which mine multiple metals out of the same deposit. And certainly up in the Silver Valley, I mentioned silver, but they're actually lead zinc deposits. And so they will, it's one metal at a time in terms of the concentration, like the flotation cell. So the flotation process, they'll typically fine tune the reagent that they use for a specific mineral. Just generally I'd call it a surfactant. They got 100 of them, but for that process of flotation, it's basically, the sulfide minerals sort of adhere to the bubbles. And so it's kind of like just making a bubble bath. But some minerals will adhere to the bubble, and then if they change the pH or something, another sulfide mineral might float to the bottom. And so they use, it's called differential flotation. So they'll change the chemistry, take out one metal at a time, and then run the process again to take out the other metal, something like that.
Bubble metals. At what point do you consider that like solution that you have left in tailings, I guess?
You don't want your, it's actually called the pregnant solution. I don't know why, but you don't want the solution with the good stuff in it to go to your tailings. You're losing money if that happens. So what they'll do is they'll just have an industrial flow sheet that, you know, separates the solution, pipes it off in one direction, and the tailings are piped off in another, or something like that. And how they do it, there's a lot of different ways to actually separate. Flotation is one of the most common for sulfide ores. But you can also use density settling. So like if you have coarse gold, gold being really, really heavy or dense, you might, if it's native gold, you could separate that out in a gravity circuit of some type to get that. And then you might, you know, run the solution without the gold in it through something else to get out whatever else it is. So a metallurgist and a mining engineer, the metallurgist particularly, or chemical engineer, would be the ones to design those kind of flow sheets. And it's really got to be different for each operation. So for example, rare earth minerals are really complicated because it's similar chemical properties for this group of 12 or 15 elements. And so to separate the individual rare earth elements, it's usually some kind of resin or ion exchange. And it may be very pH dependent, and they might have to do a very complex series of hydrometallurgical steps to separate each one. That's way more complicated than gold and silver, which are simple, or even base metals.
Yes, please.
For reclamation and restoration, the botany mining permitting and application process, what, do they bond in? Or
Yeah.
Is that how they do it compared to like where federal government and taxpayer dollars have funded some of the Superfund site cleanups from the past? How are we avoiding that through bonding? Is that still an issue?
The question was about bonding for reclamation. Is that done? As opposed to, say, a Superfund type program where the government ended up paying? Yes, and on federal land, whether it's Forest Service or Bureau of Land Management managed, or on state land, there is a bond required for reclamation, and how that's calculated and what type of bonding assurance is given is a current issue. It's the Superfund situation started a couple of decades ago, and that funding was initially generated by companies, particularly chemical companies, paying a particular amount, I don't know how it was calculated, to the federal government to set up this Superfund to cover uncovered liabilities if the company went bankrupt or no longer existed. That fund has kind of been used up, and for reasons I don't understand, it was never really reauthorized to require the companies to continue paying into that, as I understand the federal policy. But certainly in Idaho, and I think in all other states, the state requires a bond of some sort as does, say, the Forest Service, if it's on their land, so. I'm not sure about other countries. I think other countries do too.
I might go on that a little bit, but how does this bonding work? And how does a company start when you have in Idaho various projects that come in, discoveries, and typically they're not companies that have the money to go for 100 million or multiple $100 million of bonding. So how does this work?
I'm not an expert on that. The question was about how bonding works and companies that don't have hundreds of millions of dollars for it. There are ways in our state regulations, for example, that calculate bonding on like a per acre basis or a per something. It is a tricky one because there's always potential for unforeseen obligations or unforeseen events. Often cases, the bonding is actually underwritten by maybe not a bank, but some other financial assurance. So it's kind of like taking out insurance. And it's fairly, I won't say it's controversial, but it's fairly technical as how, what is an adequate bond? Because you're right in that a lot of these companies do not have tremendous financial resources. And so they're kind of depending on the money they're going to get from the actual mining to help pay for the reclamation. Now, if the price goes down, maybe they're not going to, or the cost of mining is higher than they expected, then they could end up kind of short. And so there's different ways of doing financial assurances, and I'm by no means an expert. I think in the last few years, Department of Lands, which in Idaho is the agency that runs it, has redone some of their bonding requirements, partly to make it more flexible.
We have time for maybe one more question. This is not, there is a question, Dr. Crowley.
Thank you, as always. Dr. McLean last week just sort of floated a quick mention of a project that folks that he's part of, I think in Nevada, where I think it was a uranium project, which they were doing sort of in what sounded a lot like the idea was it was a bunch of drilling, but then they were going to pump through some kind of reagent or gas. And given one of the things that you've reminded me of today, right, which is the extent to which the tailings are a big part of the challenge, that sounds like a very nifty project. Can you expand on Dr. McLean's story?
Sure, a little bit. Yeah, the question was based on last week's speaker talking about a uranium project where they pump solution down and somehow recover it. Basically what he's talking about, it sounds like, and I obviously didn't hear it, is what's called in situ mining, which I didn't really go into, but that is another kind of mining. And it's where you have to have an element like uranium, which is readily soluble in some kind of not too nasty fluid. You can also do this with copper mining in a waste dump or something, the sulfuric acid leach. For uranium, there's actually a number of uranium mines that use in situ leaching because uranium is pretty oxidized, or if it's oxidized, it's quite soluble. And so you have like a well field where you pump a solution down in one location, it travels through the rock, and then it's pumped out in another well. And presumably after the solution has gone through the uranium area and picked up some of the uranium. And that can be done in, you wouldn't necessarily want to do it in tailings. unless you screwed up somewhere along the way. But you can, it is done in waste rock dumps, and it's a little bit like another process called heap leach, where you sprinkle cyanide solution on top of a bed of crushed rock. It percolates down and dissolves and captures the gold, which the solution of which is collected on plastic and pipes at the bottom of the heap. I think there's probably a lot of work going on right now and better ways to do solution mining of all types. It's a lot cheaper and definitely useful in some situations, uranium being one.
Thank you. And then the controversy probably is about the not so nasty solution and using cyanide and going after it. So, but anyway, well, thank you all for participating. Most of all, thank you for Dr. Gellerman. Let's give her another round of applause, and we'll see you here on Thursday. Thank you very much.